Imagine that two robots are playing a game of Connect 4. Red won the coin toss, so red goes first, and then yellow goes next, and then red goes again, and so on. Since they're computers, they never make a mistake, so red's obviously going to block that. Oh, no, wait, hold on. Something's wrong here. Let's try again. Okay, this time our robots are actual perfect Connect 4 players, so there shouldn't be any bad moves like last time. All they have to do is flip the coin to see who goes first. Looks like that's tails, so yellow goes first. And, oh, game's already over. Okay, now they flip the coin again. Now they're flipping the coin a third time. And there doesn't seem to be much actual Connect 4 playing going on here, huh? It seems like as soon as the robots know who goes first, they know who wins the game. So there's not much point in actually playing the game, is there? What's going on here? It all started with a German mathematician named Ernst Zermelo. Zermelo was one of the first people to think about two-player games from the point of view of mathematical logic. Specifically, he was interested in analyzing chess. In 1913, he wrote this paper, which translates to On an Application of Set Theory to the Theory of the Game of Chess. One of his results, now known as Zermelo's theorem, says that exactly one of the following three things is true about chess. Either white can always win, black can always win, or both players can prevent each other from winning, thereby forcing a draw. When we say that one player can always win, what we really mean is that that player has a winning strategy. A strategy is like a function that takes as input the current state of the game and outputs the move that that player should make. If our players are computers, you can think about their strategies like they're programming. A player has a winning strategy if their strategy guarantees that they will win, regardless of what moves their opponent makes. For example, let's consider this tic-tac-toe board. It's your turn, and you're playing as the X's. Feel free to pause the video here and try to find a winning strategy. Okay, so for those of you following along, if you chose to put an X in the lower right corner, then you probably found a winning strategy. Your opponent can go in any of the 4 remaining spaces, but regardless of where they go, you can always place an X somewhere to guarantee that you win. If they go in the upper left corner, you place it in the upper right corner. If they go in the upper right corner, you put your X in the upper left corner. Regardless of what they do, you still win the game. That wasn't the only possible winning strategy you could have found either. If you go in the upper right corner first, you can still win the game. Because no matter where your opponent goes, there's always somewhere you can put an X to get 3 X's in a row. It's really similar to the first winning strategy, but a little bit different. So if you found either of these two strategies, good job. One important feature that Connect 4, chess, and tic-tac-toe are all lacking is any sort of randomness or hidden information. Games that involve flipping coins, rolling dice, or shuffling cards are much less likely to have winning strategies, since the extra element of randomness might prevent one player from always being able to win. In general, we're going to be considering combinatorial games, which are games that satisfy the following conditions. Condition number 1, there are exactly 2 players. Condition number 2, players have perfect information about the state of the game, which means no secrets like face-down cards, for example. Condition number 3, there are no elements of random chance in the game, like rolling dice or flipping coins. And condition number 4, very important, the game must eventually end. If the game doesn't end, then nobody can win the game. There's an optional 5th condition that the game can't end in a draw, and we'll get to that in a second. Remember Zermelo's theorem from earlier? It turns out that Zermelo's theorem applies to a lot more games than just chess. In fact, Zermelo's theorem has since been more generally applied to any combinatorial game. In other words, If two people play a combinatorial game with perfect strategy, either one player must have a winning strategy, or the game must end in a draw. If the game satisfies the fifth extra condition that draws are impossible, then we are actually guaranteed that one player has a winning strategy. For the rest of this video, we're going to assume that our games always have a winner and a loser, so that no games ever end in draws. You might be suspicious of this assumption, but it really isn't that unreasonable. Even if the normal rules of a game allow for ties, as is often the case when players are competing for the highest score, you can usually find a tiebreaker or a series of tiebreakers to ensure that one player wins. Here are a few of my favorites. In the game of Go, players place black or white stones to capture area. The more area you control, the more points you get. But, as is true for a lot of games, the first player to move has a real advantage. To compensate for this, the player who goes second is given some number of extra points, called a komi. The komi is almost always a fractional amount of points, like 6.5 or 7.5, to ensure that the players never tie. This is a simple, but in my opinion, quite clever way to build a tiebreaker into your game. Here's a more modern example. In the game Canvas, players build mini paintings out of transparent plastic cards. Points are awarded based on different combinations of cards. If players end up with the same amount of points, and the first tiebreaker fails to distinguish them, then the second tiebreaker is to, quote, have a neutral person judge the artwork of the tied players and declare a winner, end quote. And last but not least, here's my favorite tiebreaker. The game Arboretum involves players using cards to build grids of trees and scoring points based on the arrangement of different numbers and species among their grids. As in Canvas, if two players end up with the same score, there's an initial tiebreaker that can distinguish them. However, if that tiebreaker fails, then this is the backup tiebreaker. Quote, the players must each plant a tree. In 5 years' time, the player whose tree has grown the tallest wins. I've played a few games of Arboretum over the years, and this hasn't happened to me yet, but I'm still waiting. Also, if there's another game that has a fun tiebreaker that you like, feel free to share it in the comments. I'd love to hear about them. Okay, now it's time for something that looks a little bit more like math. Logic is the branch of math that deals with the truth or falsity of statements. For example, 2 plus 2 equals 4. That's a true statement. 9 is a prime number. That's a false statement. There are no odd perfect numbers is a statement that we don't quite know the truth value of yet. It could be true, it could be false. First order logic is the branch of math that deals with the truth or falsity of statements with the quantifiers for all and there exists inside them. For example, for all real numbers x squared is greater than 0. This statement is claiming that if you plug in any number for x, then x squared should be greater than 0. This is almost true, except that x could be 0, and if you plug in 0 for x, you get 0 is greater than 0, which isn't true. Therefore, we say that the statement as a whole is also false. Another false statement is there exists a largest natural number, because there is no biggest number. As an example of a true statement, for all integers x, there exists a y such that x plus y is 0. This one is true because if I take any number for x, like 4, then choosing y equals negative 4 ensures that x plus y is 0, since 4 plus negative 4 is 0. Since this works for any value of x, we would say that the statement as a whole is true. Whenever we're writing down statements in first order logic, we'll often abbreviate for all with this upside down A symbol, and there exists with this backwards E symbol. This is what our 3 previous examples look like using this notation. Notice how this last example, there exists a largest natural number, has this sneaky second quantifier in the symbolic definition, even though it didn't appear in the English definition. Now, we've finally reached the connection between the two halves of this video. If I have a winning strategy, that means that there exists a move that I can make, such that, for all moves my opponent could make, there exists a move that I can make, such that for all moves my opponent could make, etc., etc., there exists a move that I can make, such that I win the game. In other words, saying that I have a winning strategy in some combinatorial game is just like saying that some first-order logic statement must be true. We can write that in symbols using X's to denote moves that I can make, and O's to denote moves that my opponent could make. The analogy here is supposed to be with tic-tac-toe. And then the content of the first-order logic statement is some function W of all of the moves that basically says, do I win the game given that I played these moves and my opponent played these other moves? I think this is best illustrated with an example. Let's think about tic-tac-toe again. If you're the starting player, you have 9 different moves that you can make. After you make one of those, your opponent then has 8 moves that they can make. And after they make one of those, you have 7 moves, etc., etc. If we want to formalize this in terms of first-order logic, then we're going to end up with a statement that has 9 quantifiers for the 9 possible moves that can happen in a game of tic-tac-toe. There is one small issue that I should bring up with this process of translating a game into a first-order logic statement. The game does have to be guaranteed to end after some fixed number n moves. Otherwise, our first-order statement would have to be infinitely long, and we're not going to deal with that today. This correspondence doesn't only go one direction, though. It turns out that any first-order logic statement we can also interpret as a 2-player game. Basically, anytime we see there exists an x, that means that we choose the value of x. And anytime we see for all O, that means that our opponent is choosing the value of O. We win the game if the statement ends up being true, and otherwise our opponent wins the game if the statement ends up being false. For the last time, here are a few examples. The statement there exists an x1 such that for all O1, x1 is greater than O1 is a game that I like to call the highest number game. It starts with us picking a number, for example, 100. Then our opponent gets to choose another number, for example, 101. Our opponent then wins because 100 is not greater than 101. So we lost this game. Let's see what happens when we swap the order of the quantifiers, though. This essentially forces our opponent to go first. Now our opponent starts by picking a number, like 1 million, but we get to then choose a bigger number, like 2 million. This time we win the game, because 2 million is greater than 1 million. Notice how changing the order of the quantifiers changed the truth value of the statement, just like changing the order of players in a game might determine who wins. This last example is pretty advanced, so feel free to skip it. It's the end of the video anyway. But if you've seen the epsilon delta definition of continuity, then maybe this will help this make a little bit more sense to you. A real valued function is continuous at some input a if, for all epsilon greater than 0, there exists a delta greater than 0, such that for all values of x, if x is within delta of a, then f of x is within epsilon of f of a. How does this statement look like as a game? Let's assume our function is f of x equals x squared, and we're checking continuity at the value a equals 4. Our opponent starts by picking some positive number epsilon, like 0.5. Then, we choose a suitable positive number delta, and in this case, I've chosen delta equals 0.05 because I happen to know that it works. Now, our opponent can pick any number x that is within delta of a equals 4, for example, x equals 3.96. This actually means that we win this game, because the distance between 3.96 squared and 4 squared is 0.3184, which is less than 0.5, and that's all that matters. Remember that just doing this one example isn't enough to prove that f is continuous at a equals 4. What we actually need to prove here is that we can win this game every time, regardless of what moves our opponent makes. And that's it. Thanks for sticking around for that last example. Here are the 3 things that you might take away from this video. 1. Every combinatorial game has a winning strategy for one of the players, as long as there aren't any draws. But figuring out that winning strategy might be hard. 2. Every statement in first-order logic is either true or false. But again, figuring out whether that statement is true or false might be pretty hard. And 3. You can turn any game into a statement, and you can turn any statement back into a game, so they're basically the same thing. Next time you find yourself staring at a math theorem, maybe try turning it into a game. And that's all for today. Thanks for watching.